And today we're going to have a quick review of the CMOS technology, and then we'll talk about some industry trends. As I mentioned, in this course we'll emphasize a lot on the industry trend. So we want to make this to be technology relevant, for the future. So first of all, we look at the MOSFET structure. And I assume that you are familiar with this. And so this is a schematic of a planar 2D MOSFET from the side view and the top view. So this is actually the layout. So you have the W and you have the L. So those are the design parameters for circuit designer. And then we have the contact to the source and drain. So those will be the contact. And then the principle for the CMOS technology is that we have both MOS and PMOS. And MOS, electrons are conducting, and PMOS, holes are conducting. And those two are complementary. That means all the operations are opposites, let's say with different polarity. MOS use positive voltage, gate voltage to turn on, PMOS use negative voltage to turn on. So I think those concepts are familiar to you. You are familiar with that. So then we have this CMOS technology to have both MOS and PMOS on the same substrate. So typically it's a P-type substrate for the MOS. And when you make the PMOS, you have to make an N-well. You have to dope the N-well, and then you make PMOS there. So this is MOS, this is PMOS. And here we also show the body contact to the NMOS. So you have P plus body for the NMOS and N plus body for the PMOS. So I assume these are the prerequisites for this course. So I'll skip that. But when you look at the MOSFET operation, actually we prefer to use this band diagram to explain what's going on inside the device. And this is 3D view of the band diagram. So here, this is for NMOS, and let's say, we tilt the transistor by 90 degrees. So you are looking at this side is a silicon substrate, and then this is the gate, this is source, and this is the drain. So this is deep into the substrate. And in the band diagram, let's look at the conduction band edge. And here this is a EC, conduction band edge, and then EV, the valence band edge. And then in the middle is the Fermi level, intrinsic Fermi level. But of course, for the system, you only have one Fermi level, which is stationary. And the source and the drain, essentially, are the reservoirs for the electrons. You have many electrons here. And the P-type region under the gate essentially form the two PN junctions. Let's say source to the channel and channel to the drain are two PN junctions. So you have this barrier. And in the off state, when the gate voltage and drain voltage are zero, so those electrons are separated and you don't have any current flow. So what happens is when you apply gate voltage, the band is bending so towards the surface. So the barrier height is reduced at the silicon surface, which is the interface between the oxide and the silicon substrate. And then the electrons will diffuse out from the reservoir because the barrier is lowered. But still the current is zero if the drain voltage is zero. Because source and drain have the same equal potential. So then they will diffuse out, but those two diffusion current will cancel each other. So the net current is zero. And then you apply drain voltage, then the drain band will be further lowered, then you will have this kind of band edge at the surface of the silicon. So now the electrons will move over the barrier, and then they will fall down to the drain. It's like water. So electrons are like water. So they are trying to go to lower potential. So then the electrons try to move over the barrier and then be accelerated by the drain voltage and then eventually collected by the drain. So this is how the drift current occurs in this MOSFET structure when you have the on state. So this is how the MOSFET work actually. So any questions? And then you should be familiar with those IV characteristics for the MOSFET. There are two kinds of IV. One is ID versus VD. This ID, VD. This is also the output characteristics of the transistor. And then we have the ID, VG. This is called the transconductance, transfer characteristics of the transistor. So this is drain current with respect to the gate voltage. And here we have different operation region. So in the IDVD, we have this turning point, which is the separation between the triode and the saturation region. And as you know, for today's transistor, the current will not saturate. So you still have some slope when the VDS is larger than the saturation voltage. And then for the IDVG, you will get the threshold voltage here. So I assume you are familiar with those concepts. And there are some parameters associated with this IDVD curve. So first of all, if you look at the triode region here, because in the triode region, the transistor is more like a resistor. When the VDS is small, so the transistor is more like a resistor. So you can take the slope, because current is kind of proportional to the voltage, right? So that is a resistor. Resistor, you know, is a linear relationship between the current and the voltage. So then you can take the slope here. This is a channel resistance for the channel. The slope is the on-state resistance for the channel in the triode region. And we use big R on for this one. And then this is another slope. Okay. If you bias your transistor here, and then take the slope in the saturation region, you will get another slope. So this is called the output resistance. My question is, what's the difference between this output resistance and on resistance? Any idea? So this output resistance is a concept for analog circuits, small signal model. So because you are biasing the transistor here with a DC bias, and then you vary your AC signals here. So it's small signal parameters typically used for analog circuits. And for digital circuits, then you don't have that concept. Then for digital circuits, you look at this on resistance. And then there are some other concepts, like on-state current is defined as when the gate voltage, VGS, equals to the drain voltage, VDS, equals to VDD. So this is the maximum current you can get out from the transistor. This is defined as on-state current, I on. And in the IDVG curve, not this curve, but you can get this transconductance GM, which is also important for analog circuit design, because that is kind of the transconductance from the, let's say, the gate voltage, how much you can translate to the drain current. So this is also important for the analog circuits, but I don't think that will be used for our lectures here. Okay, so then let's go to the subthreshold slope. And below the threshold voltage, the transistor is in this so-called subthreshold region. And if you plot the ID versus VG in log scale, so here this in log scale, okay, then the IV will look like this. And this is I-on, because as we discussed, this is when the gate voltage equals to VDD, and then let's assume the VD also equals to VDD. Then this is maximum current I-on. But this is the threshold voltage. Below the threshold voltage, ideally, the transistor's current is 0, but in reality, it's not 0. The current, drain current, will exponentially decay as you reduce the gate voltage below the threshold. But it will not become 0. Okay. So here, when the gate voltage becomes 0, still you have some current. Okay. But I have to say this is when the VD equals to VDD in this case. VG equals to 0. So there's still current here, and this current is I off, defined as I off. When the gate voltage equals to 0, drain voltage equals to VDD, then there's still some current flowing, then this is defined as I off. Of course, when the drain voltage becomes 0, gate voltage becomes 0, then of course current is 0. But here the drain voltage is not 0, so then still you have some current. So this is the exponential decay function here, and we define the slope here is the subthreshold slope, and it's typically represented by, let's say, 60 millivolts per decade. So what does that mean? That means this slope tells you if you want to reduce your current by 1 order of magnitude, or by 1 decade, you need to reduce the voltage, gate voltage, by 60 millivolts. This is due to the thermodynamics, due to the Boltzmann distribution of the carrier's concentration. So that's how we get this number. But let's say this S, if you express the S into this equation, then you will get this S is defined as the slope, and actually it's 1 over the slope. And it has 2 components for the S. The first one is the gate voltage versus the phi S is actually the surface potential of the transistor. I will not go into the details. This is very device basics. This phi S is the surface potential. So basically, I can still quickly describe that. Okay. So the gate voltage, and then and the channel surface